Happy to be here. I have two lectures, and what I'm going to do in the first lecture, I'm going to describe the algorithms we actually use to simulate plasmas. And in the second lecture, we'll get to applications, hopefully. So the main point of this these lectures is to alert you that a new kind of window on understanding astrophysical plasmas is opening in recent years, mainly due to the tremendous advances in the capability of computers. So what I'm going to talk about is ab initio calculations of plasma physics. And this is a field that's been developed for plasma physics applications for, say, laser plasma interaction or accelerator physics over the years. It's been developed since actually 1950s, as we'll see. And only in recent years have computers caught up with the algorithms. And we're now able to run relatively large three-dimensional simulations, which really help to understand the fundamental physics. So the outline of the lecture is I'll explain a few examples where plasma physics on computers is interesting, and then I'll describe the methods we use to simulate plasma physics on computers. In particular, I'll be talking about this method called particle in cell, or PIC, which you will find that it's very similar to what you've heard earlier today or in the previous lectures. It's a variant of particle mesh method. It's a variant of particle mesh method for a system that has not only positive mass, say the gravitational mass in the particle mesh method that was discussed earlier today is always positive, right? In plasmas, we actually have negative masses. So by mass, I mean charge. So we'll have particles with positive charge, particles with negative charge. And that's the fundamental difference between a gravitational particle mesh method and a plasma physical particle mesh method. And so I'll describe two types of simulations that have been developed. One is what's known as electrostatic particle in cell method, and then electromagnetic particle in cell method. They're essentially they're cousins working on different time scales. So if your problem doesn't involve very rapid changes, doesn't involve relativistic motion of charges, then you can deal with electrostatic codes. And if you actually require some large time dependence or relativistic motion of charges, then you want to do actually solve full electromagnetic system of equations. OK, so of course, as you all know, plasma is the fourth state of matter, ionized gas, which is permeating most of the universe. And what we want to understand with plasma physics is the peculiar properties of ionized gases that appear when you allow these gases to abstract from just single particle motion, but actually look at collective effects that happen in the plasma. So these collective effects are extremely important in many astrophysical and plasma physical applications. And they really hold the key to microscopic physics that happens underneath most of the approximation we use in astrophysics. So for instance, hydrodynamics, or MHD, are really large-scale approximations to plasma physics. What happens on smallest scales is what's described by kinetic equations. And this is the kind of physics we're trying to solve here. So in the astrophysical context, the physics of smallest scales that happens in plasma is responsible for controlling, say, reconnection of magnetic fields, which is a property that's treated fairly ad hoc in say, MHD or any other method. But with a ab initio particle in cell simulation, you can actually address the intrinsic rates of reconnection. You can also address the physics of resistivities, and these are important for ultimate dissipation of turbulent cascades. So if you have a cascade of turbulence on large scales, it eventually goes down to smaller and smaller scales, eventually dissipates, and that dissipation is governed by the electromagnetic interactions between particles. So physics of transport and heating, and in particular in astrophysics in recent years, the importance of two-temperature plasmas has been raised. So you can have plasmas where ions and electrons seem to be at different temperatures, and the physics of such environments can be addressed with direct kinetic plasma simulations. Okay, so when we talk about plasmas, we want to define what times and spatial scales we're dealing with. So there are several important scales. One of them is called plasma frequency, which essentially is the fastest frequency a plasma can respond to if you try to perturb a plasma. So essentially, a plasma frequency is what happens if you take, let's say, a background of positive ions and displace electrons to one side. So they will feel a returning force, returning electric field that will try to pull electrons back, and then they will undergo harmonic oscillation. And that harmonic oscillation goes with the plasma frequency, which scales as the square root of the density of the plasma, the charge of the charged species, and inversely with the square root of the mass of the species. So the electrons, as you can see, having the smallest mass, will have the largest frequency of ringing in the plasma. Associated with this plasma oscillation is this length scale, which is called the Debye length, which is the ratio of the thermal velocity divided by the plasma frequency. So effectively, what this length does for you, it describes on which scales charges can screen each other. So if you put an extra charge into the plasma, then that charge will attract, so let's say you put an extra positive charge into the plasma, it will try to attract the negative charges towards it, and the scale on which the extra electric field from this new charge is canceled out in the plasma is given by this Debye length. As you can see, it's sensitive to temperature. The reason is that if you have very cold plasma, then it's very easy for electrons to get attracted to the extra charge. So then the Debye length will be shorter. You will have a clump of electrons surrounding your extra ions. If electrons are rapidly flying around, it will be harder for the extra charge to exert a pull on the electrons. So this Debye length will grow. Okay. Another interesting length scale is the skin depth, which is the speed of light divided by the plasma frequency. This is probably familiar to you from courses in electromagnetism. This is basically the length over which an electromagnetic wave would penetrate into a conductor. So if the conductor is reflecting an electromagnetic wave, there is a exponential fall off of the field as you go inside of the conductor, the skin effect. And this is the typical scale on which those fields will dissipate. Another time scale is the Larmor frequency. So this is the frequency of gyration if you have magnetic fields. And this can be modified for relativistic effect if you add the gamma factor in the denominator. OK, so the Larmor frequency is pretty straightforward. OK, so then we can try to order all of these spatial and time scales in the plasma and see where we stand in a typical environment. So what's shown here are the typical ordering of time scales and typical ordering of length scales. So the time scales, the shortest time scale is the plasma plasma oscillation timescale of the electrons. Then for typical parameters, the next scale would be the Larmor gyration of the electrons. Okay? Then the ions come in. So the ions are obviously much heavier, so their time scales for plasma oscillation and the gyration are longer. So here they are. And then we go into various waves that can propagate in the plasma. So alpha wave, or the ion sound wave over here. So this is a typical ordering for the for these waves. And in a typical plasma, the longest time scale over here, what's drawn here is the electron-ion collision time scale. So as you can see, all of these interactions or all of these time scales happen in a collision-less regime. So the typical time for large angle scatter of an electron on an ion will take much longer than any of these modes. Okay, so the range of time scales captured here from the alpha wave time scale and on is well described by fluid models. So you can derive equations of hydrodynamics or MHD, and they will well capture the alpha mode and the sound waves and so forth. So if you're interested on time scales that are this long, then you're better off with a fluid model. If you're interested in the shortest time scales, the time scales that have to do with the plasma frequency of electrons or the gyration of electrons, then you have to use fully kinetic models. And if you're interested in something in between, which is to say you're not interested in the plasma oscillations of the electrons, but you are interested in the dynamics of the ions, then you may deal with a hybrid method. So hybrid method treats electrons as a fluid and treats ions fully kinetically as particles. Okay, so corresponding to these time scales, there are length scales. And again, so corresponding to the plasma oscillation, there is a Debye length, and then there is Larmor radius, the skin depths of electrons, the Larmor radius of ions, the skin depths of ions, and so forth. So, so basically, these fully kinetic models are really applicable in the shortest time scale and smallest length scale limit. And on an astrophysical scale, these scales are ridiculously small. That's why most of the that's why this field hasn't really picked up until now, because you're going to waste a lot of computing resources trying to resolve something extremely small. How small? The typical skin depths in an astrophysical plasma is 6 kilometers. Okay, so we're dealing with length scales of 6 kilometers, and typical astrophysical scales are parsecs, right? So obviously, this is not going to go very far. I'm not going to simulate the whole interstellar medium with the kinetic code. However, there are special regions in the plasma where kinetics is very important, and you don't have to simulate the whole, many parsecs. You can actually, most of the physics happens on a few gyroradii or a few skin depths of ions and electrons, and that's the scales we want to work with. Okay, so one slightly confusing notion is notion about collisions. So you can go ahead and calculate what's the typical cross section for a particle collision is, and then ask what kind of plasma do you need to have when you have to care about individual particle collisions. And what you find out is that, kind of paradoxically, the denser your plasma is, the less you have to worry about collisions. And the reason for that is the following. So imagine a particle in an ionized gas. If the gas is very rarefied, then the particle motion is basically a straight line until it encounters some other particle and scatters off. So the individual particle collisions are actually important in this case. If you had many particles in the plasma, and they were all exerting little pulls on this particle, then those pulls will on average cancel out. So you don't really have to worry about plasma collisions if your plasma is sufficiently dense. If it's too dense, of course, you will go into the solid regime, and then you really have to worry about collisions. But there is a certain limit which most of the astrophysical plasma satisfy, which is this parameter, the Debye parameter, or the number of particles in the Debye cube. If it's very large, then you don't have to worry about individual particle collisions. Okay, so you can treat it as a collective interaction. And so this figure of merit, this Debye number, so the density times the cube of the Debye length, is shown in this plot. Over here, you probably can't read it, but basically for the interstellar gas, this number is about 10 to the 8. So for solar corona is about 10 to the 6. Diffuse hot plasma, 10 to the 5. If you get into some of the laboratory plasmas, then it can get kind of iffy. So you can get about 100, or if you have laser plasma interaction, can get up to tens. So you may worry about collisions in these cases. But in most of the astrophysical environments, this number is sufficiently large that you don't have to worry about collisions that much. OK, so how do we actually go about modeling these plasmas? So one way to think about this is we're basically solving the system of what's known Vlasov-Maxwell equations. So this is a system that describes the evolution of a distribution function. So distribution function is the density of particles in phase space. This equation describes the evolution of the distribution function, basically saying that the phase space volume is conserved. So what you have here is this is called the Vlasov equation. So this is the Lorentz force, and this is the spatial and the velocity derivatives of the distribution function. And coupled with this are equations for the evolution of electric and the magnetic field. So the divergence of the electric field is just given by the charge, and that's just the first moment of the distribution function. So we take the velocity moment of the distribution function, integrate velocities out, we get the density. That's your Poisson equation. For the Ampere's law, we have here the current, and the current is velocity moment of the distribution function, so v times f, integrated over the velocity. That's your current. And then you have two other Maxwell's equations, so the divergence of B equals 0 and the induction equation. OK, so with this, this is a closed system, and you can go ahead and try to solve it. The problem is it's in general a 6-dimensional system. This function is defined in 6 dimensions, 3 space, 3 velocities. And up until now, the efforts to solve this directly on the computer have been kind of futile. It may change over the years. Brute force approaches can actually eventually win if your computers become large. But so far, this just direct attack on this problem has been rather not fruitful. The alternative is to solve this equation using particles. So the meaning of that is that we're actually not solving just a function, the distribution function itself. We're sampling it with many particles, each particle representing a piece of this phase space. And then we're evolving these particles using the Lorentz force. And we're relying on the fact that along a particle trajectory, the distribution function is conserved. So particle trajectory is basically a characteristic of this Vlasov-Maxwell system. So for a given particle, we can solve its equation of motion. Here it's written in a non-relativistic form. So dv dt is just the Lorentz force, electric and the magnetic forces. And then dx dt is just the motion of the particle. And then this has to be coupled with the Maxwell's equations. Okay? And again, so this is the standard Maxwell's equations, where the current and the charge density can be extracted back from the individual particles. So if you just had point particles, you would say that these are delta functions in space. Then the charge density is the sum over a lot of delta functions, each having a charge of an individual particle. The current will be, again, the same thing, bunch of delta functions, each moving with some velocity. Okay? So this is what formally looks like a decent way of solving this Vlasov-Maxwell equation system. Okay, so in order to solve this using point particles, you will find that you will run into the two types of issues. First of all, if you really are dealing with point particles, you will have to worry about their intrinsic interactions. So you will run into the granular noise due to the fact that you have relatively few particles, much fewer particles than you have in a real plasma. So you have to worry that this debye number is large enough so that individual particle collisions are not affecting your integration. Also, what you're effectively doing is you're computing the force between particles. And the easiest way to compute the force is using this particle mesh analogy. So we're basically going to reintroduce the mesh in order to compute the electric and magnetic fields on the mesh, and then use those fields to advect particles through the mesh. So basically, what we're doing is we're taking a point particle and trying to spread it out in a finite size particle, and that eliminates the granularity associated with each individual delta function. And then we're going to use a grid in order to record the electric and magnetic fields and use the grid to solve the electromagnetic fields rather than individual two-body interaction. Okay. So typical algorithm goes something like this. Let's say this is a particle on a grid. You would deposit its charges onto the grid points. So different pieces of this charge would end up on different points on the grid, depending on how close it is to each individual grid point. So this way, you would collect the charges onto the grid. Then you would solve the Maxwell's equations. You would solve the electric fields, for example, from these charges. And then you would interpolate the electric fields back to the location of the particle and move the particle on with the Maxwell, with the Lorentz force. A crucial piece of advice here is that this step is called the deposition. So the deposition of charge has certain way of depositing charge on each individual grid point. So there are certain sum of linear coefficients that you're assigning to different pieces of the grid. And then in order to interpolate the electric field back to the location of the particle, you're also using some sort of coefficients, probably linear coefficients, trying to connect particle to the grid points. So in order to have the best types of codes actually have the same weighting. So the weighting that goes to the grid has to be the same as the weighting that goes from the grid back to the particle. If you don't do this, you may end up with funny things like self-force. So particles sitting on the grid would suddenly start to move even if there are no other particles. Okay, so this is something to keep in mind. OK, so how do we deal with collisions here? So if you actually had point particles, then the collisions are really due to the short-range interactions. So the fact that Q over R, the force increases quite rapidly as you go towards the location of the particle. So this should be R squared, of course. So the short-range interaction is what gives you collisions. The long-range interaction is what gives you collective effects, right? So what we want in our simulations is to actually reduce this short-range interaction, mainly because we cannot put an Avogadro's number of particles onto the grid. So we're forced to use smaller number of particles. Therefore, these individual short-range collisions could be important. So in order to eliminate them even more, we're using this idea of a spread particle. So if a particle is not a point particle, but rather has a certain shape, then what you're doing is you're effectively suppressing the short-range interaction. The force actually turns off and becomes 0 right in the middle of the particle. Okay? So for us, this is good. If you were trying to do a gravitational simulation, this could be bad, right? Because you actually want the large angle scatters in the gravitational simulation. We don't care about that. So we actually want to have a collision-less plasma with as few particles as possible. So again, assigning the shape of the particle when you allocate the charge to the grid determines the way this force is cutting off as you get to the center of the force. And the smoother the shape is, the smaller this force it becomes.
How do you choose the optimal shape?
So basically, it's a trade-off. There is no optimal shape. The more smoother you make the shape, the more expensive it is to calculate. So it's a trade-off. You just find what is acceptable to you for the number of particles you're willing to put in. So typically, people don't go beyond second-order splines. You could go much more elaborate, but then it becomes much more expensive because you have to compute this shape or use this shape on every particle, and you can push billions of particles in the simulation. OK, so the typical simulation flow is sort of like this. So you load your particle distribution. You push the particles according to the electromagnetic fields that are on the grid. Then you, given the new locations and velocity of the particles, you compute the charges and the currents on the grid. Then you have a Maxwell equation solver that, given these charges and currents, can give you back out the new electric and magnetic fields, because charges and currents are just sources for the electromagnetic fields. And then you have new E and B fields. You compute the force, and you go back, and that's your complete time loop.
You're not going to get the diversion of BB zero?
Sorry, could you repeat that?
Diversion of BB zero?
OK. So we'll get to that. That's a very important question. For now, we're going to deal with just electrostatic codes where we don't worry about the evolution of the magnetic field. But it is an important question. OK, so just to give you a bit of a background on names and history of this subject. So the whole thing started essentially in 1950s with John Dawson, who was, I think, at Princeton at the time, but then was later at UCLA. He began computer experiments in the 1950s with, imagine that, right? So it already sounds impressive. But he did essentially one-dimensional electrostatic plasma simulations, where what he said is that we have a one-dimensional domain, and every charge is going to be a sheet of charge. So it's essentially a transverse sheet of charge that is allowed to move in this one dimension. It has a particular peculiarities, right? Because if you have two sheets of charge, it doesn't matter how close they are to each other, because the electric field is just like a field between two capacitors. So, but still, he was able to compute a lot of the fundamental plasma physics that comes about when you say try to have two particle distributions interpenetrate each other. So he computed all of these electrostatic two-stream instabilities and Landau damping, all of these effects.
Is that the same man, young and old?
This?
Yes.
No, this is a different man. So this is John Dawson. This is Oscar Buneman. So in 1960s, Hockney and then Buneman basically introduced the way to solve these electrostatic Poisson equations. So they introduced the Poisson solvers. Actually, I think Oscar Buneman even invented the fast Fourier transform, but he never published it. And then, so in the 1970s, the actual theory of electrostatic particle and cell code was developed. So what I mean by theory is that you can read plasma physics books where all of the waves and dispersion relations are derived in a very rigorous fashion. You can do exactly the same thing with the computer plasma. So you can derive all the equations for the waves and the modes and the instabilities using the discretized form of the plasma equations. And that was done in the 1970s. And then sort of beginning in the 70s and 80s and 90s, we went from electrostatic codes to electromagnetic codes. So where we solved not only the Poisson equation, we also solved the electromagnetic fields using the full Maxwell's equations. And these two important books came out. So Hockney and Eastwood, Computer Simulation Using Particles, and then Birdsell and Langdon, Plasma Physics via Computer Simulation. So these books have several editions, and I think they're called the Pig Bibles in this field. So the reason, so essentially the electromagnetic simulations were already existing in the early 70s, yet the computers just weren't large enough to do much with them. So let me just give you a few background information on how these codes work in practice. So let's start with electrostatic codes. And we'll discuss the time stepping we use and the shapes of the particles, how they affect the simulation. OK, so electrostatic simulation is very simple in the sense that we don't have these fancy Maxwell equations. All we have is the Poisson equation. So we have del squared of the potential equals to the charge density. The electric field can be derived from the potential, and then the force is just the electric field. And so the loop is very similar again. You move the particles, you compute the charges, you solve the Poisson equation, interpolate the electric fields, and repeat. And when you actually want to integrate it in time, you have to worry about what kind of integration method you want to use. And you want to make sure that your numerical method for integration has convergence and accuracy, and it's a stable method. And if all of this works, you actually want it to be efficient as well. And the method that of choice that seems to be used in most of the plasma research is the famous Leapfrog that was described in much detail in the last few days. And essentially what we have is we're decentering the velocities and the positions in time. So a velocity would be evaluated where the the velocity is decentered with respect to the position, so that when the position has to be advected forward, the velocity is available right at that time step, half a time step. And that, as you heard, this is a simplest symplectic integrator, and it has a very good properties in terms of time reversibility. And it turns out it also has a very good energy conservation properties, even though it's not necessarily obvious why it should. OK, so if you try to solve the simplest oscillation problem with the Leapfrog method. So basically, we're solving an oscillator equation. So d squared x dt squared is omega squared x. This has the obvious harmonic solution. And then you can ask, how does the accuracy of this harmonic solution depend on your time step that you chose? And what you find is that if your time step is fairly small, so omega delta t is small, then what's shown here is the frequency you actually compute versus the frequency that you should have. So you can measure what is the actual frequency of your oscillation of a particle. And you will find that for, of course, small enough time steps, you'll have a perfectly correct solution. As you get to larger and larger time steps, you have a phase error. So you predict a different frequency than what you should have. And then if your omega delta t is larger than 2, your code explodes. Okay, so this is where the stability limit of the Leapfrog is reached. Essentially, what happens is you have a harmonic oscillator, and if you put too few points per one oscillation, then it will try to jump from one end to the other end of your oscillation, and it will go unstable. This happens very robustly in a few time steps. So it's a rite of passage to actually try this with your PIC code and see how it quickly explodes. All right, so time integration is fairly straightforward here. What about charge deposition? So the simplest way charge can be deposited onto the grid is what's known as the nearest grid point method. Basically, if these two charges are in the same grid point, we just call their charge to be in this grid point, and we just assign it to this one. And this charge is in this grid point, we assign it to this location. This is a fine method of assigning charge. It turns out it's a very noisy method because if this particle moves from this grid point, so let's say it's infinitesimally inside here to infinitesimally inside here, the charge will suddenly jump by a significant amount from one cell to another. So another way of doing this is using this cloud and cell algorithm, where you essentially say that the particle shape is distributed over some distance. Let's say it's a cell, and then the part of the particle that falls on this cell is going to be assigned to this grid point. Part of the particle on this cell is going to be assigned there. And so effectively, the charge deposition looks like a triangle. So as a particle moves through the grid, you will have a triangular charge moving through. OK, so you can go more fancy, and instead of a flat top, you can have a triangle for the particle shape. You can have a spline. You can have a very smooth spline. And effectively, what this does to you is it eliminates higher harmonics. So if you look in the Fourier space, so Fourier transform of this shape of the charge has ringing at high k numbers. So it has short wavelengths contributions to the charge density. You make the charge smoother and smoother, these short wavelength contributions die off, and correspondingly, this is more and more expensive to compute this type of a shape function, as I mentioned before. So it helps to think about these it helps to think about these shape functions in the Fourier space, because there you can easily see how the sharpness of these corners starts to introduce the short frequency noise. And why the short frequency, spatial frequency noise is important is because the grid cannot tolerate, cannot resolve something that's on scale smaller than a few grid points, right? So when you try to resolve something when you try to put in a wavelength that is shorter than a few grid points, the grid will just randomly assign that to some other wave mode. So it's called aliasing. So if you if you have some spurious high-frequency fluctuations and you try to put them on the grid, to you it looks like you just you put in a wave, yet the grid will not be able to resolve that wave, and it will put this wave power into some other modes. So it will put it into different wavelengths where you didn't actually, you weren't supposed to put any power into it. So so the high frequency, the high K components of the shape function is what introduces noise in the simulation. And you can beat this with in two ways. This noise can be beat by either making a smoother and smoother shape function, which is more expensive per particle, or you can just throw more particles at it. So if you put more and more particles, then these individual spikes due to the short frequency from one bad shape function will actually average out. So depending on what your computer resources are, you may either go with this direction or with that direction. OK, so when we solve the Poisson equation, you can think of it as solving it in the Fourier space. So this is the second order derivative of the potential equals to the charge density. You can finite difference it, and so you can either solve this using the matrix equation, or you can solve this using the Fourier transforms. So you can Fourier transform this like this. So you will have 1 over k squared from the divergence, from the del squared. And then you can invert this equation in the Fourier space and get the potential. And then you can get the electric field as well. But what you notice is that what in Fourier space looks like a k vector, in the numerical space looks like a modified k vector. So the modification is due to the discretization of your grid. So the actual discrete Fourier transform looks something like this, whereas the analytical Fourier transform looks something like that. So both of them are just Fourier transforms of the charge density divided by different k. And this k is a modified wave vector due to the discretization effects. OK. And then another way to see the aliasing is that if your Fourier transform of the charge density has short wavelengths power, which is on scales that are shorter than the grid scale over 2, so the k grid is the typical wavelengths you can actually resolve on the grid, then that power will map back into the space that you can actually resolve, and it will add to the power over here, and this is the unphysical noise that starts to appear. OK, so in short, you can actually, as I said was done in the 70s, you can go ahead and reformulate your whole Vlasov-Maxwell equation in terms of these shape functions. So you can discretize you can say that the force is interpolated from electric fields using this shape function, and the divergence of the electric field will be computed as well using this shape function and so forth. And what you find is that the plasma frequency of your problem, so the fundamental oscillation, will be modified by the shape function of your Fourier transform of the shape function of your charge. So effectively, the plasma oscillation, if we had no discretization errors, then the omega squared would be just equal to the omega p squared. Yet it gets modified by this factor, which is related to it's a Fourier transform of the shape of your particle. And you can go ahead and actually compute the whole theory of plasma dispersion relations using this discretized plasma description. And you will find that it looks very similar to what a normal plasma physics looks like, except there are these modifications due to the shape functions that are appearing everywhere. OK, so in terms of restrictions on the time step and the spatial lengths, the Courant condition restricts your time step. So if you actually are resolving the speed of light, as we would do in the electromagnetic simulation, then the time step has to be smaller than the speed of light divided by the sorry. So time step should be smaller than this thing divided by the speed of light. So basically, this is the if this is a two-dimensional simulation, then this is the delta x in one direction. This is delta x in the second direction. And what this is saying is that this is a diagonal on the grid. So time step has to be smaller than the light propagation through a grid. And then the maximal frequency oscillate in the system, which is in our case is the plasma frequency. A good fiducial number is keeping that smaller than 0.25. As we saw, if you have it equals or larger to 2, then this explodes. The leapfrog will explode. In a typical simulation, having it smaller than a quarter is a good idea. And again, you don't want the particle to move faster than more than one cell at a time. OK, now let's talk about the electromagnetic codes. And as an example, I will use the algorithm that I use in my code, which is called Tristan MP. But basically, the same algorithm is used in many other electromagnetic codes. So the main difference for the electromagnetic codes is that your equations are more complicated. So you're no longer solving the electrostatic Poisson equation, which is just this guy. You also have the induction equation and the Ampere's law. And typically, your equations for particle motion are relativistic. So you want to allow for the particles moving close to the speed of light. The loop of the evolution is still the same. So we're still advecting the particles, extrapolating to the grid, and then returning the turning currents into the electromagnetic fields. So how do we actually do this? First, let's talk about time evolution. So the electric and magnetic fields, let's talk about the way we solve the Maxwell's equations first. So what you want to solve are these two dynamical equations, dE dt and dB dt. And again, for them, we use Leapfrog as well. So they're decentered in time, but they're also decentered with respect to each other. This is the time centering of all quantities in a typical electromagnetic code. So electric and magnetic field are decentered by half a time step. The particle position and particle velocity are decentered by half a time step. And the way it's arranged is so that you can see here that in order to compute the time derivative of electric field, you need the curl of the magnetic field. So that's why E and B are decentered in time. So when you know the magnetic field, you can compute its spatial derivatives very easily. And then the electric field will jump over the curl of the magnetic field. And then when you need to compute the evolution of B, the curl of the electric field is ready to be computed in space as well. And then B can jump over the electric field. So it's centered well in time that way. And then the way the particles are decentered makes it easy to compute the current right when you need it. So if the position and the velocity are decentered like this, you know the velocity in this step. And the velocity translates directly to the current. And you need the current right in this moment to advect the electric field. So the current should be computed right where the curl of the magnetic field lives in time. Okay? So that gives you a nicely leapfrogged, staggered way of putting it all in time. Now, what about spatial discretization? So in order to evolve the Maxwell's equations, we use what's known as a finite difference time domain method, or FDTD. And it's discretizing electromagnetic fields on a grid where they're not only decentered in time, they're also decentered in space. And what I mean by that is the following. So let's see. Here is a slightly larger plot. So the electric fields are, each component of the electric field is defined in different places on the edges of the grid. So let's say if this is the y direction, this EY is going to be defined here, EX is going to be defined here, EZ is going to be defined in the middle of this edge. Okay? And then the magnetic fields are defined in the middle of the faces. Okay? So the magnetic field is transverse to the face, in the middle of the face, over there, and over there. Okay, so why do we do this? The reason is that Maxwell equations are very easy to reformulate this in terms of circuit integrals. So if you, let's see, do I have this? Let's look at the original Maxwell's equations again. So imagine you integrate this over an area. Imagine you integrate this over a circuit. Okay, so the integral over no, never mind. Sorry. That's right. Thank you. So if you integrate this over an area, this would be an integral over a circuit of the electric field. Okay, so dB ds, so the integral of B ds would be an integral of electric field over a circuit. Let's go back to the grid. So an integral of the magnetic field over the area of this edge would be an integral sum of the electric fields going around the edges of this surface. Okay, so if we can evolve the integral of the magnetic field over the surface just by computing the circulation of the electric field around the edges of this grid. And the same is true for going the other way, evolving the electric field. So electric field is a circulation of the magnetic. So evolution of electric field is equals to the change in the electric field equals to the circulation of the magnetic field, and that's why the magnetic fields are decentered with respect to the electric fields. Okay, so this is called the E-mesh, and the same idea is used in MHD codes. In the code that Jim Stone works with, the same idea is used. We actually go slightly to more extreme. In normal MHDs, you don't have to worry about the electric evolution equation. You only have to worry about the induction equation. And we actually have to worry about the Ampere's law. So we have both electric and magnetic field evolution using this E-mesh. Okay. This electromagnetic solver has various interesting properties, one of which is numerical dispersion relation. So what's shown here is the numerical phase the numerical frequency that you compute for a given wavelength of an electromagnetic wave, just calculated with this finite difference time domain method. So we just send the electromagnetic wave without any plasma and send it through the grid. And what you find is that depending on the wavelengths that you put on the grid, the smaller the k vector is, the longer the wavelengths, the better resolved you are, the better your agreement is with the analytics. And analytics here would be a straight line, 45 degrees, speed of light. If you try to under-resolve your wave, so you put shorter and shorter wavelengths on the grid, then you start getting phase errors. And you can see that this blue curve, the the numerical velocity of light actually becomes smaller than the physical velocity of light. Okay, so your electromagnetic wave can propagate slower than it should through the grid for the shortest wavelengths. Okay, so there is a numerical dispersion that's intrinsically introduced by these methods. Also, this numerical dispersion is anisotropic. So you get the best dispersion relation going along the diagonal of the grid. Along the edges of the grid, you get the worst dispersion relation. In general, this doesn't cause a lot of problems if you resolve your wavelengths. But in a relativistic plasma simulation, you can run into a very peculiar effect where a particle, say a relativistic particle, always moves close to the speed of light. And it moves close to the real speed of light. And you can have arbitrarily large gammas in the simulation. Then the particle will move arbitrarily close to the speed of light. Yet, there are small, short wavelengths. If there's noise in the simulation, there are short wavelengths trying to propagate on the grid, that particle will outrun these electromagnetic waves that are propagating just on the smallest scales. And then you can run into a Cherenkov problem. So the particle actually starts to pump up these electromagnetic waves. It emits Cherenkov waves at the shortest wavelengths on the grid, and it leads to a horrible instability. So in most of the times, this is not important. If you actually deal with highly relativistic flows, as I have to do for relativistic shock simulations, then you have to worry about this effect. Okay, now let's talk about, so we talked about the evolution of the electromagnetic fields. So all you need for that is just to get the currents and the charges. And in order to get the currents and the charges, you need to advect the particles. So the particle motion is advected. So we're solving this Newton-Lorentz force. And this is a general relativistic description here. So this is a form momentum of the particle. And there are, if you just try to naively discretize this, you will find that your equations are kind of implicit. So this is what happens. So let's say you want to do the leapfrog evolution. And let's call u as gamma v. Okay, so then this u will be, the time derivative will be the u at half forward time step minus half backward time step. This is the time derivative. And then the electric force is trivial. However, for the magnetic force, you have to put this velocity. Okay? And this velocity has to be defined at the same time as the magnetic field. And the problem is that our velocity and magnetic field are decentered in time. So we have to somehow find out what the velocity would have been in the mid-time step. Okay, so this intrinsic nonlinearity of the Lorentz force is what's giving this complication. And if you just naively say that this velocity is just the sum of the forward and the backward velocity, the forward step and the backward step divided by gamma, then you find that this is an implicit equation, right? So there is u at t plus delta t over 2 on the left-hand side and the same u on the right-hand side. So you have to find a way to somehow solve this implicit equation in order to extract the velocity of the particle. So, of course, you can go ahead and do something like a Runge-Kutta, right, where you don't worry about all of this. And you will run into problems. You will not conserve energy very well, and your phase will be off on say, gyration in the magnetic field. So one way to do this, to solve this implicit equation explicitly, is to apply what's known as a Boris scheme, or the Boris integration equation. So what you do is the following. So you note the following thing, that if you define the two new variables, let's call them u minus and u plus, such that u minus is the velocity you had at the original time step plus 1/2 of the electric push. So you apply 1/2 of the electric push, and u plus will be velocity at the final time step minus 1/2 of the electric push. Okay, so then you can rewrite this whole equation as u plus minus u minus on this side, and then u plus plus u minus on this side. And it's very easy to show that this equation now, so instead of the full Lorentz equation like this, where we had electric field, we absorbed that electric field into these new variables. And what you find is that when phrased in these new variables, this is nothing but a rotation of a vector. You can easily see this, that if you dot this u minus u plus minus u minus, you dot it with u minus plus u plus, okay, you will find that this will give you 0, and that means that the magnitude of u minus is the same as magnitude of u plus after this whole integration was done. So effectively what this is saying is that this vector u minus was rotated by some angle, and that angle actually has to do with magnetic rotation. So this cross B term means that we have defined some new vector, we rotated it by some angle, and that's what the magnetic rotation did. It conserved its length, and then we can use this fact to derive an explicit formula for u at t plus delta t over 2. And this is this formula. It will be an exercise for the student to actually derive it. It's not very hard. But the point is this, that so in the end, the end result depends on this parameter t prime, where t prime is related to the angle of magnetic rotation in one time step. So the angle of rotation is arctangent of this t prime, where t prime is defined as the q delta t b over gamma m. So this is related to the gyration of a particle in the magnetic field, as you can see. So this is just the phase of the how much phase it accumulates in magnetic rotation. Okay, so the nice thing about this is that you can actually overstep the cyclotron motion in this integration. So you can set up you can take the time step to be much larger than you would normally use in order to resolve the motion of a gyro orbit. If you do that, then all you're doing is that this angle theta by which you're going to jump is going to asymptote to pi over 2. So basically, instead of, if you just have a pure magnetic field and you have a particle going just in a pure magnetic field, if you discretize it, it will be a point here, point there, and so forth. So if you well resolve the orbit, you will have many of these points going around the magnetic field. Now, let's say you take a larger and larger time step, then what will happen is that you overshoot, and you basically just have a particle going back and forth with pi over 2 in phase every time. So it just jumps around the magnetic field. It doesn't quite resolve the Larmor radius, but it basically still does sort of the right thing. It keeps gyrating around the magnetic field. Okay, so that's how we do the motion of the particles. So this is fully relativistic. It can work for arbitrary gammas. The next step is how do we calculate the charges and the currents in order to from the particles in order to compute the Maxwell's equations, to solve the Maxwell equations. So it turns out that we can use one very interesting trick. Normally we have a Poisson equation to worry about, right? So we have we may be forced to solve an elliptic equation, the Poisson equation, in addition to solving the two hyperbolic equations, which are the Ampere and Faraday laws. So it turns out that Poisson equation is not necessary to be solved at every time step. And here is a proof of that. So imagine we take the Ampere's law. So dE dt is the curl B minus J. Okay? And let's take a divergence of this equation. So what we'll have is d by dt of the divergence of the electric field times equals to divergence of curl B, which is 0, right? Divergence of a curl is 0. And then on the right-hand side, we have a divergence of J. Okay? So divergence of electric field is just the charge density. And what we got here is a law of conservation of charge. Okay? So if you somehow manage to conserve charge, so d rho dt is equal to the divergence of the current, then you satisfy the Poisson equation by construction. So Poisson equation is a great thing to have as an initial condition, but then if your method maintains charge conservation, so you're not losing any charge as a particle moves through the grid, then the Poisson equation will be satisfied at all time steps afterwards. And this is a nice trick because it eliminates the need to solve the elliptic equation in a parallel simulation. Right? We want to have our simulation as local as possible to a processor. We don't want to do Fourier transforms over a large simulation. And in fact, if you think about it, this is basically how nature does this. Right? Nature doesn't worry about solving elliptic equations on infinite domains. Right? It's all local. You have a local charge motion, local radiation, and so forth. And then the electromagnetic waves propagate and establish the right balance far away. So if you manage to have a method that actually conserves charge, then you're done. And this method we use was called the charge conservative current deposition. Effectively, it calculates the volume that a particle sweeps as it moves from one grid point to another grid point, maybe through several grid points. I mean, if you cut a corner here, you can, in one step, you can move through several grid points. But in general, what you do is you compute how much, in this case, it's 2D, so we compute how much area has crossed from this cell to that cell, how much area has crossed from this cell to that cell, and so forth. And this calculates how much current is flowing through an interface. OK, so let me show you an example of how this works. OK, how do I grab this thing? OK, so what's shown here is what I did here is I put two particles, electron and a positron, one on top of each other. So they were sitting right here. And then what I did is I took one of the particles and I started moving it away from the original location. And it's moving at a fairly mildly relativistic velocity, so gamma is 1.4. Okay? And what you're seeing here are the vectors of the electric field that get established between the two charges. Okay? So the color here is EY component. So it's a vertical component of the electric field. And the color here is the EX component. And the vectors show you the actual shape of the electric field lines. So what I'm doing here is I'm solving the Maxwell's equations with this finite difference time domain method. And I'm depositing the current using this charge conservative current deposition. So as a particle moves through the grid, its charge is moving with it as far as the grid is concerned. And so let's continue this. OK, so what you're seeing is basically what you would expect. There are two charges that are connected by electric field lines, and they just move out. So this is a periodic box. That's why you're seeing this field coming back from the other side. All right, so now let's try to make it more interesting, and let's look at gamma that's larger. Let's take gamma 14, for example. Really hard to type when you don't see what you're doing. Okay. You know what? Let me turn this off for a second, then I'll be able to catch my terminal. Okay. All right. Okay, so now we're going to try a larger gamma particle. So what are the main differences you see? The main difference is that you're seeing a relativistic effect, right? So this charge is not moving anywhere. You can see that its electric field lines are basically going straight towards it, whereas this particle is moving relativistically. So you can see a bunching of the electric field lines because of the relativistic effect. So you can see that most of the field is in a sheet connected perpendicular to the direction of motion. Okay, so this shows you how the Maxwell equations can be solved together with the current from the particle. And so the next step, of course, is to put many particles in, and then you have the full PIC simulation. And so let me just talk about, next time I'll mention more things about how you actually make this works in terms of parallelization and boundary condition and so forth. But I want to mention just a few codes that are actually in existence right now and their advantages and disadvantages. So in general, you don't have to go out and reinvent the wheel if you have a particular plasma physics question you want to address. You may have to pay some money for it, but there are some public codes available. So this website is the Berkeley Plasma Simulation Group, which maintains several public codes. They are going from electrostatic codes, so XES1 is electrostatic code. There are codes that simulate plasma devices, so you can actually have some sort of a plasma processing apparatus, say, where you fry a microchip with plasma, and you can attach circuits to it, and so forth. And the code that we'll be using in the session, on the practical session, is the XUPIC code, which is a two-dimensional relativistic particle and cell code. Sometimes it's called 2.5-dimensional because the particle motion is restricted in 2 dimensions, but the particle motion can be in 3 dimensions, but the fields are only restricted to be in 2. So the variation of the field is restricted to be in 2 dimensions. Okay, so XUPIC is a public code. There is also this more commercial version called UPIC Pro, which is the one I recommend we download. It's probably easiest to install if you just want to use it for a few days. There are also 3-dimensional codes like Warpal, and Tristan is a public code, and it will be released real soon now as a public code as well. So it's a 3D parallel code, particle and cell code. Then there is UCLA group is using Osiris code, which is mainly used for plasma accelerator research. And you will hear a talk about another code called VPIC next Thursday, I think, which is a Los Alamos code that is pretty generic particle and cell code. So all of these are used by different communities. So the public codes can be used by anybody, but basically they're all tuned to slightly different constituencies. So if if the code is mainly tuned towards laser plasma interaction, it may not have as generic boundary conditions as say, an astrophysical code would have, or the other way around. OK, so to finish off, let me just show you an example of a plasma simulation using this UPIC Pro code. So let me just show how this works. So we start out by loading an example input file, and it goes ahead and creates a lot of windows. Most of these windows are useful.
You're being recorded, you know.
I'm not afraid of them. They're my friends. OK, so what's shown here, so what this is going to be is going to be an example of a beam plasma interaction. So you have over here electrons in the background plasma into which there's going to be a flying electron beam. So electron beam will start from this boundary here. It will flow into the box, and it will excite what's called a plasma wake, or an oscillation in the plasma. So it's running right now on my laptop. And what you're seeing here is the green is the electron beam. Electron beam is penetrating the plasma here. And here you can see what electrons in the plasma are doing. So the electric field of this electron beam is blowing this plasma apart. And you can see that it's flying out. But then the ions which are left behind are starting to attract these electrons back. So they're starting to come back, and they're kind of going around this electron beam. And then behind this, you're going to get an oscillation in the plasma. So you basically deflected the electrons, and now they're going to ring back and create a plasma oscillation. Inside of that plasma oscillation, there is very strong electric fields. And these very strong electric fields are actually proposed to be used for particle acceleration, like a future tabletop plasma accelerator. What happened here is that the simulation switched into what's known as a moving window frame. So right now, the electron beam doesn't look like it's going anywhere because our frame is shifting. We went into the frame that's sitting on the electron beam, basically. And this new plasma is coming in and getting deflected. And you're seeing this plasma wake established behind this beam. And then a few particles in these accelerating regions can actually gain quite a bit of energy. And we'll play with this type of simulation more in the discussion section. But there is a whole bunch of diagnostics that exists in this code. So you can show phase space. You can show the actual positions of particles. You can show the electromagnetic fields, the history of electromagnetic energies, and so forth. So a lot of diagnostics here. Of course, sometimes in the prepackaged code, you don't have exactly what you want. But for the simplest things we're going to do this week, it's going to be sufficient. So I guess I'll stop here. And next time, we'll discuss the actual applications of these methods to the astrophysical plasma simulations. Thanks.